Today we ask the question, what drives molecular diffusion? And as a corollary to this question, we also consider the most convenient and proper description of molecular diffusion. The presentation today is an abridged version of my talk on uphill diffusion that can be viewed on my YouTube channel. We start our journey in the Antarctica. Here's a picture taken in Antarctica showing fortresses of ice containing nearly pure H2O in contact with seawater that contains salt. The question arises why there is no diffusion of salt from seawater into the ice fortresses. In order to resolve the paradox observed in Antarctica, let us resort to the Gibbsian thermodynamics of phase equilibrium. For two phases that are in thermodynamic equilibrium, the chemical potential of any component must be equal in either phase. The chemical potential of any component is written as the chemical potential in some standard state plus R times T times ln of the activity, where the activity is the activity coefficient times the mole fraction. The chemical potential is the partial molar Gibbs free energy, where the Gibbs free energy has two contributions, the enthalpic contribution and the entropic contribution. These represent respectively the unmixing and the mixing tendencies when the system is subject to perturbations in composition. S is the entropy and is given by the Boltzmann equation. S is K ln W that is engraved on his tombstone in Vienna. The symbol W stands for Wahrscheinlichkeit. You will note that Josiah Willard Gibbs and Ludwig Boltzmann were contemporaries. The red line shown here is a plot of the Gibbs free energy for the ice crystals, plotted as a function of the mole fraction of sodium chloride. The blue line is the Gibbs free energy of seawater plotted against the mole fraction of sodium chloride. The seawater contains significantly higher concentrations of sodium chloride. The phase equilibrium between the ice fortresses and seawater is described by the common tangent between the two curves. And this tangent intercepts the x1 equal to 0 axis at this point, which represents the chemical potential of water in the ice that is also equal to the chemical potential of H2O in seawater. At the other end, the common tangent intersects the x1 equal to 1 axis, at which the chemical potential of NaCl in ice is equal to the chemical potential of NaCl in seawater. what we note is that there is equilibrium between the ice fortresses and seawater, but this equilibrium corresponds to significant differences in the salt concentration in the ice fortress and in seawater. This example underscores the fact that the mole fraction differences or mole fraction gradients are not the proper driving forces for molecular diffusion. In view of the arguments presented in the foregoing slides, we must abandon the commonly used Fick's law to relate the molar diffusion flux to the gradient of the concentration. In setting up the proper flux driving force relationship, we have two choices. The first one is to adopt the Onsager formulation that was coined by Lars Onsager, who won the Nobel Prize for Chemistry in 1968. In his seminal paper in 1945, he wrote, "The theory of liquid diffusion is relatively undeveloped. It is a striking symptom of the common ignorance in this field that not one of the phenomenological schemes that are fit to describe the general case of diffusion is widely known. In the Onsager formulation, the flux is related to the gradient of the chemical potential by defining a matrix of Onsager coefficients L. For an n-component mixture, we have n-1 independent fluxes and n-1 independent chemical potential gradients that are considered to be the proper driving force for diffusion. The matrix L, that is n-1 times n-1 dimensional, is asserted to be symmetric, and this symmetry relation is dubbed the Onsager reciprocal relations. My own preference in setting up the flux driving force relationship is to adopt an approach that is different from the Onsager formulation, but follows the line of thinking that was championed by both James Clerk Maxwell and Maxwell-Stefan in their papers published respectively in 1866 and 1871. Both these pioneers focused on diffusion in multi-component gaseous mixtures. The approach can be generalized to address diffusion in non-ideal fluid mixtures by replacing the partial pressure gradients by the gradients of the chemical potential. Let's consider, for example, a binary mixture of species 1 and 2. In setting up the Maxwell-Stefan formulation, we assert that the force acting on species 1, which is the negative of the gradient of the chemical potential of species 1, is balanced by the friction that species 1 experiences in undergoing a relative motion with respect to species 2. The frictional term is proportional to the differences in the diffusion velocities u1 minus u2. It should also be proportional to the relative amounts of 2 and 1, and we may take the mole fraction of 2 as a measure of the composition of the mixture. In setting up the linear relation between the chemical potential gradient and the velocity difference, we introduce a factor RT and the Maxwell-Stefan diffusivity in the denominator. So the physical significance of the Maxwell-Stefan diffusivity is that it represents an inverse drag coefficient. With this choice of multiplying factor RT, the units of D12, which represents the inverse drag coefficient between 1 and 2, has the units of square meters per second. Only one of the chemical potential gradients is independent because of the Gibbs-Duhem constraint and the fact that the mole fractions add to unity. So this is the kernel of the Maxwell-Stefan diffusion formulation. The persuasive advantage of this formulation is that it can be extended quite elegantly to much more general types of situations, as we discuss in the subsequent slide. Maxwell-Stefan diffusion formulation lends itself to generalization to a variety of scenarios that are encountered in practice in two different ways. Firstly, if there are additional driving forces that act on species 1, for example, pressure gradients or electrostatic gradients, these are to be added to the left-hand side. So the generalized driving force that causes diffusion of species 1 is the isothermal isobaric gradient of the chemical potential plus a term that is proportional to the pressure gradient plus another term that is proportional to the electrostatic potential gradient. F is the Faraday constant, Z is a charge number. So if I take this term and this term, I can describe diffusion in electrolyte solutions. If I take the chemical potential gradient and add the pressure gradient, I can describe the diffusion process in ultracentrifuges that is used for separation of uranium isotopes. So the generalized Maxwell-Stefan formulation asserts that the driving forces acting on a species are balanced by friction. The driving force for component 1 is balanced by the friction component 1 experiences with respect to the partner species in the mixture, component 2. This is the contribution of the frictional contribution between 1 and 3. This is between 1 and n. Furthermore, I can choose n to be the pore wall of a porous material. And if I do this, I recover the equations that describe diffusion in porous media, and as a special case, the Maxwell-Stefan formulation reduces to the dusty gas model for gaseous mixtures. This is the driving force friction relation for component 1. I can similarly write the appropriate relation for component 2, etc. We note that due to the Gibbs-Duhem constraint, only n-1 of the driving forces are independent. If the species are charged, I also have the electroneutrality constraint. Indeed, the Maxwell-Stefan formulation yields the well-known Nernst-Planck relationship as a special case. Here are the major takeaways from this presentation. The gradients of the chemical potential are the proper driving forces for diffusion. The Maxwell-Stefan diffusion formulation is the most convenient one. The Maxwell-Stefan diffusibilities are independent of the reference velocity frame. The Maxwell-Stefan diffusivity has the significance of an inverse drag coefficient. And an important fact is that the inverse drag coefficient d12 is independent of the reference velocity frame. The Maxwell-Stefan formulation can be intuitively extended to include additional driving forces, for example, pressure gradients, electrostatic potential gradients, and also additional species in the mixture. In the pore walls of a porous medium, such as zeolites or metal organic frameworks, can be considered to be a pseudo-species in the mixture. Indeed, the Maxwell-Stefan formulation is the most convenient one to describe diffusion inside zeolites and morphs.